products also capture the geometry of a vector space by defining the angle between two vectors. We examine this idea in this video. If we take a look at the Cauchy-Schwarz inequality and use that to define an angle in an inner product space between two vectors, this actually coincides a little bit with our intuition about 2 and 3 dimensions. So if the norm of x and the norm of y are not 0, then the Cauchy-Schwarz inequality tells us that -1 has to be less or equal to the inner product of xy divided by the norm of x and the norm of y, and that has to be less or equal to 1. So if you look at the diagram on the right, we can see then that there's a unique value w between 0 and pi, so that cosine w is always equal to that quotient of the inner product over the norms. That number w is then the angle between the vectors x and y. Intuitively, that angle tells us how similar in orientation the two vectors are. In fact, we can go ahead and write this out again using the dot product, so that cosine w is equal to x dot y divided by the norm of x and the norm of y. Let's go ahead and compute a couple of angles. First, we'll start by computing the angle between the vector 1, 1 and the vector y, 1, 2. The length of x is going to be 1 squared plus 1 squared, so root 2. And the length of y is going to be similarly root 5, which means x dot y over the norm of x times the norm of y is going to be 1,1.12 divided by root 2 and root 5. So we end up with 1 plus 2 is 3 in the numerator, root 2 times root 5, which is root 10 in the denominator. And so cosine w is going to be 3 over root 10. Taking inverse cosines on both sides, we get that w is equal to cosine inverse of 3 over root 10. In our second example, we're going to find the angle between the vector x, 1, 1, and the vector y, 1, -1. Both of these vectors have length root 2, and so in this case, cosine w is going to be the dot product of 1, 1 and 1, -1 divided by root 2 times root 2. This gives us 0 over 2. Means the angle between these two vectors is inverse cosine of 0, or 90 degrees. And if we look at these two vectors and we plot them in R2, they are in fact perpendicular. So in this example, the actual physical happenings of the math agree with our intuitive idea of what perpendicular vectors should look like. A key feature of the inner product is that it also allows us to characterize vectors that are orthogonal. Two vectors x and y are said to be orthogonal if and only if their inner product is 0. If additionally the norm of x and y are both 1, then the vectors are said to be unit vectors. Unit vectors that are orthogonal are called orthonormal. Orthogonality is the generalization of the concept of perpendicularity to bilinear forms that do not have the dot product. In our context, geometrically, we can think of orthogonal vectors as having a right angle with respect to a specific inner product. An n by n square matrix A is an orthogonal matrix if and only if its columns are orthogonal, so that A transpose A is equal to the identity matrix is equal to AA transpose. This also means that for orthogonal matrix, A transpose is going to be equal to A inverse. Transformations by orthogonal matrices are special because the length of the vector x is not changed when transforming it using an orthogonal matrix. Multiplying a vector by an orthogonal matrix, we get the norm of ax, and let's square it for the sake of simplicity. The norm of ax squared is equal to ax transpose times ax, which is equal to x transpose A transpose times A times x. And because A transpose A is equal to the identity matrix, we end up with x transpose x, which is really the norm of x squared. And again, the reason we square both sides here is just to eliminate the square root. So it's for easier math. Moreover, the angle between any two vectors x and y, as measured by their inner product, is also unchanged when transforming both of them using an orthogonal matrix. Here we see that cosine of w is going to be ax transpose times ay over the norm of ax times the norm of ay, which we know then is x transpose A transpose times A times y. And using the previous calculation, our denominator is going to simplify to just norm of x times norm of y. Our A transpose A will cancel in the middle as the identity matrix. We end up with x transpose y over norm of x and norm of y. So this means that orthogonal matrices preserve both angles and distances, which is kind of neat. It turns out that orthogonal matrices define transformations that are both rotations and flips. In future videos, we're going to talk about rotating vectors using orthogonal matrices.